So, the micron scale modeling uh, consists of a two-layer that we can see here, and the rotational scanning strategy at each layer. So, the first layer, including the longitudinal scanning track with 0 degree, and the second layer is the transverse, has the transverse scanning track with respect to the first layer. Here, the process parameters and the geometry and the material type for this modeling uh, is shown. So the material type is the Inconel 718, which is the uh, very famous superalloy using in the industry. The dimension of the representative volume is 600 micron into 300 micron, and the thickness of the layer is 30 micron. And laser power is 285 watt. The laser velocity is 1000 millimeter per second, and the hatching space, the distance between each track is 100 micron. So it means that at the first layer, we are going to have just 3 scans of the track, and in the second layer, we are going to have uh, 6 tracks that the distance between each track is 100 micron. And the heat source model that we used in this simulation is the Goldak double ellipsoid. As you know, there are lots of uh, heat source type that you can use. If you go through the literature, you can find the different heat source modeling. But uh, you know, the most important part of the heat source is to calibrating. I mean, when you want to use any type of heat source, you have to calibrate the dimension of the heat source according to the experiments. Technically, when the parts are uh, fabricated, a single track, uh, a single track, uh, I mean, is manufactured, is fabricated, and the melt pool dimension, including the height and the width of the melt pool, are measured. Uh, that we can use that data for calibrating our model. And also, although according to the different process parameters for different material, you can find the melt pool dimension in the literature. So I mean, the most important part of using the type of heat source is to calibrating the heat source. Uh, so here I just put the equation for the flux for the according based on the Goldak double ellipsoid. I will explain this uh, equation when we want to define it through the subroutine. But keep in your mind, this is the ellipsoid uh, shape of the Goldak heat source, including the 3 dimensions A, B, A, B, and C. So, okay, from this slide, I'm going to start uh, uh, modeling of the micron scale. So as you see, we have here a two layer for the micron scale modeling, the two representative volume. So we need to define a layer with the 30 micron thickness and 600 micron length and 300 micron width. So the units that I used in this modeling is based on the metric. So the dimensions are in meter, because you will see in the material properties definition. So I had to define the different material properties like the thermal conductivity and specific heat capacity according to the metric unit. So here, these, dimensions are based on the meter dimension, meter. So this is 600 multiplied 10 to the power of minus 6 meter, which is 600 micron. So we define a layer with a thickness of 30 micron and the length of 600 micron, and we extruded 300 micron. I will show you this on the Abaqus, the way that we define the layer. You can see here this is the section of the layer that we define. This is 30 micron thickness with 600 micron length, and it was extruded 300 micron. And we do the same for the substrate. You can see in the representative volume, it includes the two physical layers and also a substrate. So the substrate is defined with these dimensions, 130 micron into the 1000 micron, and the extrusion of the substrate is 760. We can see again the definition of the substrate here, that the section sketch is 130 micron and the length is 1000 micron, and it was extruded 760 micron. So after definition of the part modeling, we go to the material properties definition. Basically, this part of the modeling is for the partially coupled thermomechanical analysis. So it means that we first do a thermal analysis and extract the temperature distribution. So in the material properties, we define the physical properties of the Inconel 718, including the thermal conductivity, density, latent heat, and specific heat capacity.